All right, welcome back everyone to day 2 of the Cyberbot Educators Workshop. Here again is the link to the slideshow in your chat. And like on Monday, let's go ahead and click that view tab in the upper right of your Zoom window. Again, if you have 2 screens, do whatever works best. But if you're on one screen, click that view button. It's going to be in the upper right and select exit full screen view. And then you'll be able to resize your window so that, or your Zoom, so that you can have it next to your Python editor. Today, we'll start with a little bit of questions and answers, and then move on to Python scripts for navigation, followed by just a quick run through of what you'd be showing the students in terms of circuit building lessons. We'll do some sounds in there as well with a piezo speaker, and then we'll finish off with navigation by touch sensors. And your homework will be to take those touch sensors back apart and build in their place infrared object sensors that don't require touch. So first of all, does anybody have any questions?
Here's one. What slide number will we be starting on?
We are starting on, let's see, we started on slide 70. We are now on 74. Good question. Any other questions? Okay, so some that might have come up from the previous one is, some of you may have been feeling a little unsteady about servo speed and direction control, because we went through that pretty quickly. I'll go ahead and take a closer look at that with you all in just a little bit with the robot navigation. Then another thing would be the Cyberbot template.hex file. So when we when we're running Cyberbot code, the very easiest way to get started is to hit that load save button and then hit or browse for file to open something. And then in your downloads, there should be a cyberbot_template.hex file that we saved from the previous session. So I'd like you all to open that and then hit load.save and click show files and check to make sure you've got cyberbot.py down in your project files along with the main file. So give me a thumbs up once you've got that that hex file reopened. 1, 2, 3, 4. Ooh, you guys are good. See some folks still working on it. 6, 7, 8. Oh, great. Good job, everyone. Okay. So with this file, we are now ready because of the fact that we have cyberbot.py in there. We can go ahead and import the Cyberbot module, and then we can do stuff like bot of 20, write digital of 1, which is what we use to turn on that amber light below the breadboard, just to make sure that our Cyberbot board worked and was communicating with the microbit. So yes, you'll really need that because basically, if we don't have that file in there, like if I try to run this, make sure I'm plugged in here. Okay, so I'm going to put in the batteries real quick.
And you
Oh,
have a
sorry,
question?
Yeah, go ahead.
Sorry, what were the two files?
Okay, so the basically, if you hit once you've opened cyberbot_template, so that's load save or
Mhm.
browse for file, and then go through and find it from when you saved on Monday and click open. All right, and then the next thing to do is to check and make sure using load save and then show files. And you want to make sure you've got, doesn't really, the name doesn't actually matter as long as it was a file where you added the cyberbot.py module to your project files. So for that, you'll find project files and select show files, and then just verify that you've got cyberbot.py down in there.
Thank you.
Thank you for the question. All right, so I forgot that I need to have the batteries plugged in for just this quick little demo. All right, so here I am with the batteries plugged in and the power set to 1, which will be enough to turn on these lights when I run this script. So basically it runs great right now. If I, click connect and then flash, and basically this little amber light will come on. So we know the board's working. Now, if I instead just pasted this code after opening the editor. So like if I refresh this, don't do that, just watch. So if I refresh this, we get our basic starter code that shows hello world and a heart. And if we look inside here, under project files, there's not a Cyberbot module. And so if I try to connect and flash this time, basically there'll be a frowny face and then a message scrolling across the microbit. Oh, I'm sorry, no, it's displaying hello world because I forgot to paste in the previous code. So if we're running code that we're trying to use to talk with the Cyberbot as just opposed to the plain old microbit, and we flash this, now we should get a frowny face. There it is. And then a message. And to see that message without having to try to read it on the display, you can always hit open serial like so. And it'll say that it found a problem on line 2 because there's no module named Cyberbot. And so if your students see that, well, what you can do is hit load save and then look inside your project files by clicking show files, then select add file and go and find your Cyberbot MicroPython folder. And I know this is difficult to see, sorry about that. And then somewhere in there, there's going to be cyberbot.py. And when you open that into the project files, you can close out of the window, flash it again. And we're back to it working with the P20 light turning on. All right. So that's why we want to have a template file, is just because it's a lot more convenient. You can open it, and when you do open it, the cyberbot.py will already be in there. So your students won't have to remember at the start of every class to add cyberbot.py. It's much easier to just have a little file that you can go and open. And essentially they can open any previous file that worked with the Cyberbot to get started. And I should say any previous hex file. So like if I change this, so here we're making a change. Oops. Okay, I'll flash this, and then we'll call this one Cyberbot Blink. And I'll paste this to you in a second. So basically I can change this and save it. And then run it to make sure it works and I didn't make any mistakes. Okay, so now we have, a slowly blinking light on P20. So we'll paste this in for you all to try. Kind of a preview of some of the stuff we'll look at during the circuit portion. Okay, here is that script. So go ahead and try that out. And so now if I go and again, say reload my browser to start back again at the beginning, if I just pasted it in, if I just pasted that script in, it wouldn't work, but you can always just open the script, and a shortcut for anything that you've had recently open is to drag and drop it from the little downloads bar at the bottom, and it'll just load in. And remember that you will have the cyberbot.py module because you saved it as a hex file. Another thing, I think I whipped out the word or the acronym or the the abbreviation API on Monday, and I didn't explain it. Let's see here.
Coincidentally, in answering an observation that Dennis made in the chat, I just pasted the link to the Cyberbot library reference.
Well,
in the
that
chat
saves me some
window.
effort since I was going to have to navigate to it. So we'll go ahead and tell you what. Well, there it is. And I'm just going to paste this into the slides while we're at it here.
Okay.
There we go.
When you're done with that, Andy, can I ask you a question?
Yes, go ahead.
So I had to leave towards the end of Monday's session early and haven't had a chance to watch the recording. So forgive me, you already answered this, but on the power button, I'm assuming is the switch goes to the 2. Is that for the servos, the motors?
Yeah, so I was going
Okay.
to talk about that coming up a little bit. Your assumption is
Oh.
correct.
That's genius, by the way. I like that.
Yeah, yeah, we
Well,
came up with
out.
that pretty early on with the Bobot robot back in the early 2000s, maybe 2000, 2001. So position 1 powers everything except the servos, and then position 2 powers everything and the servos. And so you can set it in position 1 to load code. You can set it in position 1 to test sensors that you might be building on this area. And then you can move it to 2 as soon as you're ready to run the script. Once you've unplugged it here and you just have the battery power, then you can actually turn it off and turn it back on to restart the script. But if you stay plugged into the USB cable, you may need to go underneath there and use this little reset button right there to restart the script. It's a little bit hard to see, but it's right next to the cable under the microbit. I'll bring up a better picture of that later in just a little bit.
Oh, and just one little thing on assembly. I didn't see it. I may have missed it because I was scrambling today to put it together.
Okay.
Did it advise students not to turn the wheels with their hands?
That's a good question. I don't remember off the top of my head if we have it there, but it's okay if they turn it slow. It's not, well, students have a tendency to really get into the audio feedback thing of turning the servo at different speeds, and very within a few seconds they start like turning the wheel very rapidly and make this high-pitched winding noise. And that's always dangerous for the servo's internal gears. If they start skipping as a result of that over torque, when you wind it out like that, yeah, it can cause damage to the servos. So if we don't have a warning, we should add one. I'll just put a note to myself here.
I always like demonstrate with something else, you know, how you can power things, right? Go in reverse and generate electricity that way. But with some devices, eventually VEX ended up fixing that. But on early stuff that they did, you could actually fry the controller, like a lot of things, right? You can send electricity back into the
Yes, because a motor is a generator. It just depends on whether it's turning something for you or you're turning it. Because it can generate electricity. Servos are not really good generators. So yeah, you're not going to damage circuits downstream by turning the wheel. But it's best not to do it anyway. So yeah, that's a very good and important comment. So going back to the Cyberbot reference. So we were talking about an API, an application programming interface, and the Cyberbot library reference includes the documentation for a whole bunch of things you can add, but the Cyberbot module is the first one. And it actually goes over all the different things you can do. Like you can use write analog to make an LED a certain brightness, or even control a servo directly from the microbit as opposed to through the board. You can read analog, which is basically measure a voltage with that. And you can add detach to the end of your program so that, or to your script, so that if it isn't an infinite loop script, you can actually turn power off and back on, and it'll restart the script without you having to reach around to the reset button. So then there's digital IO, where you can write a state, write digital, that's turning a light on or turning a light off. And so that brings us to this one right here, where we're saying pin 20 of the propeller module, that's the propeller microcontroller that's underneath this breadboard, that routes to this light right here. And when we say write digital of 1, it turns it on. When we say write digital of 0, it turns it off. And just as a side note, if you had something like that, where you stay on for 1.5 seconds and then actually off for 17,500, or I'm sorry, 1.5 seconds, and then stay off for 17.5 seconds. So on for 1.5, off for 17.5. This would be the 1,000 times faster than an actual servo signal. And if you were able to use small enough values in here, you might be able to say like 1,400 to make, which would be 1,000 times slower version of making the wheel turn clockwise, or 1,600 would be 1,000 times slower version of making the wheel turn counterclockwise. And so I'll go ahead and run that. You basically get a blip and then it stays off for, oh, what's going on here? Why is it flash? Huh. I wonder if there's some kind of overflow situation going on. I'm not sure why it's still flashing as rapidly as it is. It really shouldn't be. I'll have to look into that and get back to you guys on Friday to explain why that's happening, because I didn't expect it to. I see. Okay. Basically, I messed up.
We have a question. Is that just a PWM signal?
Okay, so PWM stands for pulse width modulation. And with a DC motor, that is your classical pulse width modulated signal. Let me see if I can find something to draw a picture on. Okay. So a pulse width modulated signal. All right, so we've already done a blinking light. And if we were to graph that blinking light, it might look about like this. Okay, so where it's on half the time and off half the time, this is 1 and that's 0. Now, PWM has special ways to measure this. For example, this is basically on, we have a total cycle time. And right now it's on for half of the cycle time. And you can actually repeatedly deliver a signal to a motor, like that might be 80% of the cycle time, and the motor would go 80% of its full speed. If you instead gave it maybe an on time, and these are happening very rapidly, like maybe 50 times a second or 1,000 times a second. It varies with the motor that's controlled, but this would make it go maybe 20% of full speed. And then of course, on half the time, off half the time would be 50% of full speed. So that's a typical motor control signal. The servo control signal, I think I showed that earlier on. What the servo pays attention to is the duration of that pulse. And it's only a little longer to make it stay still and a little longer still to make it turn counterclockwise. So if this was a clockwise signal starting out, you make it longer and it has to repeat 50 times a second. It might stay still. And if you make it longer still, it'll, I'll get back to this. But the idea is that, yeah, there's 50 pulses a second, and each pulse is a specific amount of time, and that controls the servo speed and direction. Which is, sure, in the general sense, it's modulating a pulse duration or a pulse width, how wide that high time is on a graph. But it's not, I don't usually like to just straight out call it pulse width modulation, since that's usually used for motor control and brightness control.
We have other observations in here.
Okay, go ahead.
One is Kathy is mentioning an error message on the screen, but I'm not seeing the actual error message.
No, it's not letting me copy and paste, but I was able to get that error message off. Now my computer is giving me a hard time getting back to the one that I saved, the blink. So,
Okay, so keep on working on opening that up, the one that you saved. And Stephanie, let me know if Kathy needs additional assistance.
Okay.
oh,
Okay, so there's I guess just to finish this example of servo control, like the 1,000 times slower version would be correctly written like this. And so if I run this, it will go. So now it's gonna wait for 17 and a half seconds. It's not really worth watching, but I'll go ahead and paste this through just to kind of demonstrate in the very slow motion world what a servo signal would look like. So there's that. It's kind of boring, but it's also illustrative. Okay, let's move on to navigation. First off, are the servos centered? Well, your servos are all pre-centered, so it sends you on to the next activity. Servo direction. We talked about that already. And so what it shows is, hey, to put it in overdrive, counterclock or clockwise, you'd be giving it 1.3 milliseconds every 20,000ths of a second. And then servo speed -75 is actually not correct. I want to change that to -200 because that would correspond to this this timing diagram right here. Then 1.7 milliseconds would be +200, and it would correspond to this timing diagram. And so that's overdrive, highest speed you could possibly make it go. Then the students end up going through learning that, hey, if you look at the left side of the robot, which direction does the wheel need to turn to make it go forward? That's towards the breadboard here. And the answer is counterclockwise. If you look at its right side and ask the same question, the answer is that it needs to turn clockwise. And so then the students run this code where they're running the servos at actually about half speed. So they're making the servo connected to P18 turn at half speed counterclockwise. They're making the servo connected to P19 turn at about half speed clockwise. And it does that for 3 seconds before turning off the servos. And so using this, they get it to go forward. Problem is usually it curves a little bit. And so they'll have to slow one of these numbers down, make one of these numbers smaller in order to straighten out its curve so that it's a straight line forward. Every once in a while you get 2 perfectly matched servos, but that's pretty rare. And then we talk about intentional turns. So that, again, this is what the students go through, and I'll show you, or I'll run through some slides and paste you some code briefly. Interesting, I see a comment that one needed 130 and -128. That's pretty closely matched. That's quite good. I usually end up having to go by maybe 10 in order to correct it. So that's a good number. That may be also these no centering servos might be a little bit better. We'll see. They're kind of a new addition. So that's what the students do, and they do. I apologize, I didn't really talk about the turns. Where are they? Left and right turns. So they go through and they think about, how do you make a robot turn in place, and what's the code for that? And then how do you make it pivot on one wheel, and what's the script for that? And how do you make it create different kinds of arcs? And they try the code for that too. And so these are some activities they do in navigation. And I'll take you through the short version in slides. So again, we've got our clockwise and our counterclockwise for forward motion. And recap that I mentioned earlier on servo control. This first number is going to be either 18 or 19. 18 should be connected to the left servo. 19 should be connected to the right servo. And you'll need 2 of them to control both wheels, one with 18 and one with 19. If you want to go forward at half speed, the left wheel, number P18, would be 75. The right wheel is going to be 19, and you'll want to have -75 here. And then again, here's a reminder of our little continuum of servo speed. It usually plus and minus 125 is where you have some speed control, or rather between 25 and negative 25 and negative 125, and between 25 and 125. So the higher the number you give it gets here, the faster it'll go, the lower, the slower it'll go. And then likewise, the absolute value of those negative numbers work the same way. So as you get closer to negative 25, it's slower. As you get closer to positive negative 125, it's faster in the clockwise direction. So this is a nice little visual aid to get that. All right, so let's try some motor control now. So we'll try going forward for 3 seconds at half speed and stop. And you can feel free to, and the first thing we want to do is make sure that we know that our robot is going forward. And one more thing that I want to just take a side trip and check with you all on is to make sure that you're using the nylon. See the white nylon screws here? These white nylon screws are what you want to use to hold the battery pack in place. If you have another kind of screw there, I'd recommend removing it and putting in the white nylon screws using the standard blade on the parallax screwdriver. It's really important because this kind of metal screw can actually nick this plastic covering on the battery and then short the battery. That's underneath this plastic cover. It's got voltage on it, and if you short that voltage to this chassis through the battery pack, it drains the battery very quickly. The battery pack gets hot. It's not something you want. So always make sure to check your robot to make sure you've got the nylon screws here and here, and then also make sure to check your students' robots when they build them to make sure they're using nylon screws and not just any of the screws that they found in the kit. Okay, so I'm going to do like a student and kind of haphazardly just plug these guys in. Acting like I'm not following the instructions carefully. So I don't really know whether I did that right. And the answer will come when I run the script. Does it go forward for 3 seconds and stop? Or does it back up for 3 seconds and stop? So if it backs up, we'll know that these two cables are swapped, and they need to be basically unplugged, swapped, and then replugged. If it goes forward, we know they're good. And so let me go ahead and paste this to you. There you go. And I'll go ahead and try this on mine. And you'll need your all your batteries in, and you'll need the 3-position switch set to 2. And then when you load it or flash it, we hope it's going to go this way. Well, that's not good at all. Wonder if I had the cables. Caught in the wheels. I didn't want it to turn that hard for sure. Well, wonderful.
Because we're watching.
Yeah, and well, but more because I really probably should have just tested and assumed Murphy's Law was going to be in effect. Okay, well, that's good.
You're just giving us the true student experience, right?
Yeah, for some lucky student, I guess. Okay, that's very interesting, and it's way off calibration. So let's see here. That's the left servo. See if I give it a little bit more, tell it to turn really fast, what happens? Well, nothing, because I don't have the power in the right position. Okay, yeah, I've got a servo that doesn't seem like it's, yeah, it seems like I managed to pick out a defect here. All right, well, I'll have to look at that later. Hopefully all of you are having your robot just kind of go forward and maybe at a little bit of a curve. Is that pretty much what's happening for everybody? Can I get some thumbs up? Okay, got one. Oh yeah, I know Dennis has 128 and 130. It's looking good. Okay,
Here's-
JC, thumbs up. Kate. Okay, go ahead,
I'm-
Stephanie.
I'm just going to mention that the front of the robot should actually be the breadboard near the flat front of the chassis.
Yeah, so that's right here.
Yeah.
This is called the tail wheel. Or the
Every
tail
once in-
ball.
Every once in a while, someone will put the board on the chassis such that the breadboard is over the tail wheel. I call that tractor style. And it
And
makes it look a
if they
little bit like a
happen to have
tractor.
also swapped the servo ports, it actually all works properly.
So,
Okay.
And-
So everybody's got that drive forward behavior. Now, if
nope, not everyone. We
Okay.
have someone reporting one wheel spinning.
Oh, like me. This is not good. Okay, so let's see here. Interestingly, I don't even get any.
What if you tried the other set of ports and changed your code?
Yeah. Just to rule out the possibility of a bad port.
Or a bad servo?
Yeah. Wow. Okay, so for me, it may have been a bad port. So for the other person who had it just going on one wheel, there are several other things to check. But the just a sec, I'm trying to get the focus here a little bit better. Okay, hopefully that's all right. So what I did on my robot is and if your robot's already doing fine, then don't do this. But if your robot is turning on one wheel like mine did, try unplugging both cables from the 18 and 19 and put them on the 16 and 17 ports instead. These ports on the left are the 16, 17 ports. And then try, you'll also need to modify the pins. Instead of 18 and 19, you're going to have 16 and 17. And see if that works. Now, the other thing is, if only one servo is turning, it could also be an error, like maybe having it plugged in so that the cable is from top to bottom, black, red, white, instead of the way it should be, which is white, red, black. So check that first. But if you're confident that this is correctly connected, another thing that sometimes happens is you can end up shifting this way or this way a little bit on the pin, and you'll end up only covering 2 of the pins with the 3-hole socket instead of all 3. So you can also unplug it and plug it back in. And again, you can always hit the reset button underneath the microbit by the USB cable.
And with these values of 75 and -75, is a slight curve going to be expected?
Yeah, so a slight curve is expected. And if it curves to the right, if you slow down the left wheel, maybe by dropping it by 5 for starters, you might end up straightening it out. And just make a note after some trial and error as to, what your golden value is. Now, if you want it to go faster, like you can up it to 100. And it'll go a lot faster and further during the same amount of time. And then your top speed is roughly 125, somewhere in the 125 to 135 range. So if you really want to make sure that they're both going as fast as they can possibly go, you can even go as high as plus and minus 200. And that'll pretty much guarantee you're at about 60 RPMs. And it also goes pretty straight when it's at top speed. The reason I don't like to use those values is because then you can't really slow it down. Like if you wanted to slow it down or adjust it a little bit, and you've got your 125s in there, you can slow down the faster wheel. And incidentally, if it curves to the left, you would want to slow down the right wheel. And that's this one. And so you could slow it down, say, 120 and 125. And then again, it'll take some trial and error, and then make a note of the values that are good for keeping it going straight forward. And the same exercise is done in the backwards direction. So here is backwards. And here is a turn right. And here is a turn left, and I'm just going to try to give you the whole, I think I'll just give you an entire left, right, left version. So first I got to get back to what your servos are going to be. Okay, so forward, left. Okay, so left, we want 2 positive values. Right wheel is, oh wait, hold on. The right wheel, no, we want 2 negative values. And right, we'll want 2 positive values. And then does anybody want to hazard to guess what we have to do to forward to make it backwards? I didn't see anybody jump out.
we've
Let's,
got-
there we go. You got it. So instead of 75 and -75, we'll want -75 and 75, and that's backward. And we'll only make it turn for a second in each direction. All right, so I'll go ahead and then we'll want to change the name. forward, left, right, backward. And I'll paste this into you. Although after my mishap with the wheels, well, it's not going to work for me because I have the servos in another port. I'm just gonna hope it's right. Let me know if that works for you all. And
I think your stop has port 16 and 17 on it in the code. You
oh,
just
my
pasted it in.
apologies. It does. All
Good
right.
catch, Neela. And Kim. Two people caught you. They were just making sure, Andy was just making sure that you're paying attention. Right?
Yeah, it was all a ruse. Okay, so let me load this into mine and then I'll correct it. And well, actually, I think it's going to be quicker. All of you just, I forgot to change the last two lines for the stop. I forgot to change them to 18 and 19. And so, so your robot probably didn't stop. And so you'll want to have these set to 18 and 19 along with all the rest. I'm just setting them to 16 and 17 for mine. Okay. So can I get some thumbs up? Did you all get your forward, left, right, backward? Oh, good job. Excellent. Looking good. Okay, we got 4, 5, 6, 7. Oh, thank you. 8. Here we go. All right. Give me a shout out if you need any help. Otherwise, I'm going to move on. So this is the 0 turn radius version, which I mentioned earlier as 75 and 75 to rotate right, or -75 and -75 to rotate left. Now, here's where it gets kind of interesting in terms of reinforcing some of the earlier computer science lessons, like about repetitions. Because if we have something like this, where a student has a script that goes forward and then turns right, well, if you tell them to do that 4 times to draw a box, they might copy and paste this routine 3 more times to get their box, and that's kind of wasteful. So offering a little bit of extra credit to do this in a loop is a really good thing. And what that does is it reinforces the earlier lesson of count and repeat. And so this is where earlier on you did the first one, which was using this for loop, and that was part of the homework. And then, of course, further down in the page, we also have the endless repetition version of it using while true. And so, so having been familiar with this, this reinforces it, and it also gives it a physical manifestation, or a physical implementation. So we'll go ahead and paste this to you. Yeah, I don't think this was my port. I think I think I may have a bad connection on the power, the servo power. I'll have to replace my rights or my left servo during the break. See if I can then be able to keep up with you guys. All points bulletin, I think, I'm not exactly sure why, but I lost the indentation when I pasted it into, so bear with me a second. I need to set the indentation correctly before you run this. And this one you might want to run on the ground. Okay. All right. So it looks like it's running. Okay, so there is the corrected version of the script. And then I see a question, would it be an idea to introduce right left functions and calling functions? The answer is yes. As a matter of fact, it would be. And so happens that that was the next slide that we were going to jump into that. So very good question. I'll get to it in just a minute. Okay, so how are we doing with the forward, right, forward, right? I'm imagining that maybe yours isn't making a perfect 90-degree angle. It'll take some tuning on this sleep statement here, but did it go forward and then turn right 4 times? Okay, I see you're all still working on it. So how are we doing? Have you got, have you been able to verify that your robot did the maneuvers? Again, we're looking for 4 forward and turns repeated. Give me a okay, good job. Excellent. 2 thumbs up.
I would like to let Jennifer know, whose dogs are sniffing their new robot friend on the floor, that all of Parallax's small educational robots have been vetted by our cats, and in some cases sternly disciplined.
Yes. In fact, I can hear a cat in the background. Stephanie, is that Amber?
Yes, I am muting in between comments.
Is she at my office door asking to be let in?
Yes.
Not being
Mhm.
aware that I'm
not there.
across town.
Yeah.
Okay. All right. So here is the first instance of a computer science lesson reinforced by the robot. And then another one is functions. So we didn't really look at those during the homework, but I did put a link to where the it's in that same writing microbit programs tutorial where we did all the basics, the count and repeat, the math problems, the decisions. Coming after that is writing functions. And it has students try a whole bunch of scripts, and these are all just with the microbits little display. It's little display different kinds of functions. And I'll talk about a function in a minute. A function, so they'll go through this in detail. In the interest of time, a function is a piece of pre-written code that does a job. And the way it works is that your script actually starts down here. All these functions are just definitions. And so the MicroPython engine just kind of looks through this and goes, wow, those are all just definitions of functions. So I'm not going to do them. But then when it hits this forward call right down here, it says, oh, it's telling me to go find the forward function, do what it's supposed to, and then come back and move on to the next line. So it jumps to the forward function. It makes the robot go forward 3 seconds at half speed for 3 seconds. And then it comes back, and then it jumps down to the next line, which is another function call. And so it jumps up to right, and it's makes it pivot to the right in this case, because there's a 0 speed on the right servo, and the left servo is charging forward at 75. And so that's going to make it pivot on one wheel to the right. Now, functions can also accept parameters, and this again is similar to the lessons that are in writing functions. I'm just doing it with regards to the robot. So we have our straight ahead for a certain amount of time. And the difference is that the parentheses in the function definitions here and here are empty. And now we have a parameter variable. And so these parameter variables receive values. So when we say straight 1000, it stuffs 1000 into duration. And then it goes through and it makes it go forward. And then look at that, sleep duration. So sleep 1000, because it gets passed up here and then used right here. Then it jumps back right 500. So it goes and finds right and puts 500 there, sets the speeds, and then does it for 500 milliseconds instead of 1000 milliseconds. And so that's how adding parameters to your functions work. Now you can add more than one parameter. So here's basically my favorite function for writing robot code. I call it maneuver. And basically you get a left velocity, a right velocity, and a number of milliseconds. And one nicety about this function is that it takes the negative of the right wheel speed for you, so you don't have to. So you can kind of think about it as, oh, I just want to go forward at 100. So you set both wheel speeds to 100, and it does the positive 100 and negative 100 for you. And then for a duration of 2000 milliseconds or 2 seconds. And so this is a really nice one. I'll go ahead and paste this one through to you, and then we'll take a break. I just have to make sure that the indentation's correct, because it didn't come through correctly last time. And it does look right. And so there, let's have you try the maneuver function with 1, 2, 3, 4, 5, 6 calls to it.
We have a question.
Do
you
you
have a li-
have,
Do you have a lesson that uses steps rather than time?
that uses steps? Well, steps would be a stepper motor. Or some kind of motor that knows its position. Now, incidentally, do you want to talk about it, Stephanie, or should I?
Well, I also wanted to clarify first, are we talking about commands that attempt to go a certain distance rather than run for a certain amount of time?
Oh, okay, that's a good question. So Dennis, what,
'Cause these are
elaborate,
n-
please.
This is true, these are
Yeah.
not stepper motors. Yeah.
Yes, but I didn't know if it had an internal encoder that kept track of like something equivalent.
Not the stock servos. However, we have a new thing
I will get
on
the link.
learn.parallax.com. Stephanie is going to grab the link and put it into the chat. I'll navigate to it. So learn.parallax.com. And then under Python, we've got our Cyberbot. And down at the bottom in projects, we have, I think I mentioned that they are the kind of thing where you can, they're sold separately items, or sometimes they come in the kit, as is the case of the line follower, the rotating ultrasound, and the TV remote. But we just added one a few days ago called Upgrade Your Cyberbot Robot with Feedback 360 servos. These servos do have built-in encoders. They have a fourth wire. So we have 3 wire servos on the Cyberbot currently, and that's power, ground, and then the white wire is signal. There's a fourth yellow wire on the Feedback 360 servo that sends a feedback signal that the propeller microcontroller underneath this breadboard here knows how to work with in its firmware. And so after you've gone through the instructions for replacing the existing servos with the Feedback 360s, one thing is that the top speed of the Feedback 360 is 120 RPMs instead of 60 RPM. So it can go twice as fast. The other thing is you use a different function call to control the servos. It's called drive.speed, and 64,64 makes it turn at half of its full speed. And these are 64 64ths of a full wheel revolution per second if you're talking about speed, and you can go up to 128 on both wheels, or negative if you want the wheel to turn backward. Now this also does have distance control, which is where the steps come in, because a step is essentially the distance between a hole and a spoke on the wheel, or a spoke and a hole. So there's 64 of those going, there's 32 holes, and so there's 64 going around the wheel. And so each increment is 3.25 millimeters, and you can use drive go to actually control the distance each servo turns, as opposed to just setting it for a speed and going a certain amount of time. That is a sold separately item, and it's a pretty neat one. I like them a lot. They're fun to work with, and so that is a thing if you want to work with servos that have this feature, higher speed, and the ability to not only go particular distances, but also maintain particular speeds based on what you ask it to do. These are now available for the Cyberbot. And with that, let's go ahead and take a break. Let's reconvene at, let's see, it's 6 past. Let's reconvene at 14 past the hour.
And I'm going to
It's-
pause the recording.
And I'm going to fix my robot. Okay, welcome back, everyone. Let's go ahead and continue. So I'm just going to talk to you briefly about circuits, and then we'll build a circuit. And this is very brief. There's a chapter on it where the students build a couple of lights, and then they connect a couple of push buttons. And basically, there's one of the first pages is get ready to build. And if we look at that, it's got links to Breadboard Basics, which is a nice little video, a schematic symbols directory, and a resistor color codes page. And so what these pages do is first of all, it introduces, okay, if you have a breadboard, that's that white board that's on the front of your robot, how do you connect two wires together? And the answer is you choose a row of 5 sockets and plug both of those wires into that row of 5, and up to 5 wires into that row of 5 if you want to connect all 5 together. And then there's this list of schematic symbols. And so like for example, it shows you, hey, if you've got a resistor, it's going to look like this. If you have a potentiometer, it'll look like that. We give the names, the capacitor, and so on and so forth. And then last but not least, it goes into calculating resistor values. And the resistors you might have noticed in your kit, they're very small, but they also have small colored stripes. And so, and I'll talk about this. This is the student version, and I have an abbreviated version in the slideshow. So we'll take a look at that shortly. So here is an example of 2 wires that are connected together. And so again, you pick a row of 5 and you plug them in together. It doesn't matter whether they're right next to each other or on the opposite end of the row of 5, as long as it's a row of 5, you'll electrically connect the wires. You can also pick 2 different rows of 5, so long as you connect those rows together with a jumper wire. That also is a way to connect 2 wires together. Here are a couple of examples of not connected. Row of 5 below the other row of 5, that's not connected. Row of 5 on the other side of the valley from a row of 5, also not connected. For prototyping's sake, we have 5-volt sockets, 3.3-volt sockets, and ground. Those are to supply power to circuits. That's the electrical pressure that makes electrons travel through the circuit. There's also a digital to analog sockets and analog to digital sockets, so you can set voltages other than these common ones. With the D to A and with the A to D, you can measure like you had a voltmeter. These pins along the side here are digital I/O pins. And so we, for example, have been using BOT of 20, but you could connect a light circuit, for example, to P12. So here is a light circuit. This is called a resistor. This is a light emitting diode. And then there's a ground connection. And the light circuit can be controlled by a script to make it go on and off, just like the one that's built into the board, except for the students get to build it to see how and why it works. And so this is an excerpt from the student tutorial where it explains that inside the chip underneath the breadboard, to turn the light on, the chip connects the circuit that's connected to P12 to 3 volts. When it executes BOT of 12.write digital of 1, or with BOT of 12.write digital of 0, it connects that pin 12 to ground instead. And so you have ground on one end of the circuit here, follow it to the other end, there's ground, so there's no electrical pressure across the circuit, the light doesn't come on. There's some fun stuff we can do with sounds, and plugging the piezo speaker into your Cyberbot. I might tack that onto the homework, or we might do it near the end. It just depends on how much time is left. There's also a push button example where we add push buttons to the circuits and then monitor the push button and use the measurement taken by the digital IO pin of whether the push button is pressed or not to control the light. And these you can really go through at your leisure, either the more complicated one that's in the student tutorials, or this is kind of an abbreviated one to save some time during a workshop. And it also talks about how the read digital method will give you a 1 if it detects that the button is pressed, or a 0 if it detects that it's not pressed. And it's kind of a nice way to physically see how binary stuff works. So with all that said, and especially remember the rule of rows of 5. So if there's 2 things that you could take from this, one is there's a whole chapter on building circuits that, in the interest of making it through 6 hours of workshop, we're going to skip. I'll just tell you the main points, which are that resistors have color codes. So red, brown, first digit is you can look it up and see that it's 2. Second digit is also 2, so we have 22. The third stripe is brown, which is 1. That means we add 1 0. If it was red, we'd add 2 zeros, and so on. And then the gold stripe at the end is the tolerance value. And so you can have gold, silver, or no stripe. And tolerance is basically how much error is allowable within the resistor between the stripe's value and what its actual resistance value is. But in terms of the 2 things to take away, one is that there's an entire chapter of circuit stuff, and then 2 is that when you're connecting things together on the breadboard, they have to be in the same row of 5. And so let's try something on the breadboard. And in this case, we will try detecting objects using whiskers. So that's infrared. These are the whiskers. These are light sensors. And this is one infrared sensor that is used for when you're controlling it with a TV remote. So we'll try touch navigation. And again, this is an entire chapter. And what it looks like when you have it up and running is that the Cyberbot can be coming along with its whisker sensors sticking out in front of it. And when it bumps into something, like as it was monitoring a push button, it will know that it bumped into something, and then your script can make it back up and turn around. So here's what it's going to look like when you have it all built up. And what I'd like you to do first off is grab these parts right here. So you're going to be grabbing 2 whiskers, 2 3-pin headers. They're just little sets of 3 pins with a little bit of plastic holding them together. And then 2 resistors that are 220 ohm. That's red, brown. That's a small, relatively small resistance value. And then because in comparison to 10,000 ohms, that's a much larger resistance value. And that's going to be brown, black, orange. So we want 2 resistors that are brown, black, orange, 2 resistors that are red, brown, 2 3-pin headers, 2 whiskers. And so go ahead and grab all those things. Okay, and now I'm up and running. Okay, so now I'll try to catch up with you all, grabbing my parts. Incidentally, this is a situation where we're having a magnifying glass or a cell phone may be important for some of you. For example, with a cell phone, we have a magnifier app, and these are available for both Mac and and Android phones. And so what you can do is use that magnifier app to get a really close look at the parts. And that's going to come in handy when you are searching for brown, black, orange resistor stripes, for example. You can get a nice close look with a cell phone magnifier app or a normal magnifying glass.
We have a request to put back up the materials.
Sorry
Probably.
about that. There you go.
There we go. Okay, can I get some thumbs up as to if you've got all your parts? Everybody show me some thumbs up. Still see some people who are still working on it. Good job, everyone. I'll go ahead and just paste a direct link to this slide so you can keep working if you need to keep looking at it. Because I'm going to move on to construction. So what you'll want to do is hopefully we all have our standoffs on the front of the robot. So we want the front of your robot to look like this. And then these standoffs, you'll be loosening the screws that hold them on, and you'll hook one whisker around above the white nylon washer
and one whisker around below the white nylon washer. So it's going to be like that, and then just tighten them back down. So grab your parallax screwdriver, loosen up those screws by several millimeters, actually. Maybe at least a couple. Let's see how many turns that is. 1, 2, 3 turns is a good number to loosen them up. And then again, you'll hook one above the nylon washer on one side and then tighten it down. And you want to have it so that it goes parallel to the breadboard before jutting forward and outward. So when you're putting the whisker on, hook it on the screw and then make sure that the part that's coming off the screw is parallel to the breadboard. And then go ahead and hold it in place and tighten it down. Oops. And then put the other one under the nylon washer, get it parallel to the breadboard, and then tighten it down. So again, you'll be hooking the whiskers around the screw that's holding the standoff at the front of the Cyberbot. And then you'll be setting the whiskers so that as it comes out of the screw, it's parallel to the breadboard, and then tighten them both in place. And then after that, we'll start building the circuit on this page. And yes, that's slide 120 for the parts, 121 for the putting the whiskers in the standoff, and 122, which I'm pasting in right now, for the circuit. And I'm going to try to zoom in on this a little bit. And I'll also refer you to the student tutorial. That actually has them all on one page.
And I don't know if you already mentioned, but I'm assuming you want the power at 0.
Oh, I forgot to mention that. I'm terrible about that. Yes.
Oh, no,
Power
I
is
just
set-
realized it's like that.
Set the power switch to 0 before getting started. Or if you're already started, set the power switch to 0 now. Now be very careful about which row of 5 you put the parts in. Most importantly, that you get the same part in the same row of 5 as shown in the picture. I actually count down from the top and then insert my first 3-pin header, and then skip 2 more rows and then insert the second 3-pin header.
So from the circuit diagram, it looks like the chassis is connected to ground. Is that right?
That is correct. The whiskers are actually going, because by virtue of the fact that they're held by the metal standoffs and the screw, they end up making a electrical connection to the chassis. And the chassis is in fact ground because those plated holes that you see on each corner of the Cyberbot board are connected to the negative terminal of the battery pack. So that's what makes them grounded. And so, yes, it's connected to chassis ground. So let's see, 1, 2, 3, 4, 5, 6. So the 7th row down is where the upper of the 2 3-pin headers go. And then skip 2 rows. And add the, is that right? 1, 2, 3, 4, 5, 6, 7, yeah, and then 8, 9, 10. 7th and 10th rows down from the top. One of the most common mistakes I see is those red, brown 220 ohm resistors. They need to be connected to the black socket next to the P9 label and the black socket next to the P7 label. Oftentimes, if you're new to circuits, it's a common mistake to instead connect the resistor to one of the white breadboard sockets that's close to that label, and that's not what we want. Another common mistake is to let the resistors kind of rest against each other, those resistor leads. And that doesn't always cause trouble, but if you try to keep all the resistor leads, the metal resistor leads, so that they're not touching one another, that will also improve your chances of having the test script work out just right on the first try. How does that look? I see some people still working on it, so I'm not going to move on quite yet. Got one thumb up. Good job. Oh, so it says I have mine on 5 volts. The diagram showed 3.3. You got me. Either one works in this case, but yeah, we're better off having them in 3.3. Thank you. And good eye.
Along with that, then it seems like the 3.3 row and the 5 row have 1 pin in between them. Is there anything connected to that one?
No, so you're talking about in the diagram?
No, on the board itself, you see how you have the 3.3 rail and the 5 rail, and then there's 1 pin of space in between it.
Okay, so let me see. Yeah, no, those 2 sockets, the two sockets, let's see if I can get it. Hopefully that's aligning clearly enough so that you can see that this is a 3.3 volt socket and that is a 5 volt socket. I don't know
Okay,
how
thank
well
you.
that came through. Sure. Okay, so I still see some foreheads. Which means that folks are still building. Can I get some thumbs up as to who's got their circuit built? 1, 2, 3, 4, 5. Oh, you guys are doing great. Okay. So for those of you who, I'm gonna jump to a test script that okay, so I'll paste you the page of the test script first. And then I'll paste you the test script itself. And when you try this test script, it's in your chat, along with the activity from the chapter just above it that where you can find it as well. So when you flash this, what should happen is that if you push a whisker towards the post, that being the 3-pin header that's plugged into the breadboard. I just lost video here. Sorry, I'm trying to get my video back.
We can still see your regular camera. This is something.
Yeah, I might have to use that. Not sure yet. Ah, it's back. Yeah, it's gone again. And it's back. Okay, here we are. So if you push the, I think I'll try muting my Zoom camera. And let's hope that that, okay, so now my Zoom camera is muted. And,
There we go.
okay, hopefully that'll be okay. Now I'm gonna try pushing the, yes. So this is the right whisker. I guess if we want to have it so that our left and right works out, we'll have it like, oh no, it went again.
It's back.
It's okay. So yeah, if you press the right whisker against its 3-pin header, you'll see the you'll see a light on the microbit on the right side come on. And if you press the left whisker against its 3-pin header, you will see the and it looks like it's freaking out with its focus. So hopefully. All right, well, another thing we can do is maybe just unplug this camera and use the Zoom camera. Moving the Zoom camera over to where the other camera was. Boy, this has been a banner day.
Well, we are getting reports from 1, 2, 3, 4, 5 folks via the chat that their systems are up and running.
Oh, well, good job, everyone.
Yeah.
Meanwhile, I'll continue to wrestle with my select camera, Zoom camera, and all right, so yeah, we want to be able to press the right whisker against the 3-pin header and see the right light come on, and then do that for the left whisker and see the left light come on. And once it's passed that test, then you're ready to try roaming with whiskers and unplug it, set it on the floor, and try presenting your hand to the whisker as a wall.
We have some
And-
questions about the code too.
Okay. Oh, now is this about the test code? Let me go back to
What
the
does
test code.
the 4,2,9 in that code do?
Okay,
Display set
so
pixel.
this is display.setPixel, and it is column 4, row 2, brightness of 9 out of 9.
Thank you.
You're welcome. And that is again, another one where you could take copy set pixel, go to help, select documentation, and search for set pixel if your students came up to you and asked you that and you didn't have a ready answer.
I think also if you're going through and doing all of the tutorials in the series, that working with the display on the microbit is part of writing microbit programs.
Ah, that's a really good point. So
Yeah.
what Stephanie is saying is that if we go to the Cyberbot tutorial series and then
Mhm.
writing microbit programs, the LED matrix is the first one, and we just looked at scrolling text. But there's custom images down here where you can make your image using display.setPixel.
Yeah.
Thank
I
you.
know we're trying to show you in 6 hours what can be a full semester.
Yeah. So sorry that it's going kind of quickly. So let's now try the navigation by touch. I'm not sure if this script is too long. We've only got a couple minutes left, so I got to get you trying this out pretty soon here. Paste. Yeah, it pasted right through. So once you've got it working so that the light indicators show you correctly which whisker is pressed against the post, then you can try setting it on the ground. And running the script. Now, in my mind, this isn't backing up far enough to really navigate a wall properly using the script as written in the tutorial. So, but by this point, your students will have had enough experience that they will be able to go into these functions here and maybe increase the sleep time a little bit. Oh, wait. Okay, I'm going to try this and paste it to you. See if we can get some better behavior out of the robot here. Okay. So for those of you who would like a slightly better tuned version of this, I'm going to paste it in. I just changed the sleeps in the functions that make it go a certain distance and then turn. There we go. So go ahead and give me some thumbs up once you've managed to test that and that your robot's bumping into stuff, backing up and choosing a new direction properly. Excellent, Rosetta. Kate, good job. Karen, nice.
Andy, I think you have your main camera off, your main video off still.
Yes, I do. It's currently
Okay.
looking at the robot through the
Okay, never mind.
All right. Give me a shout out if you need more time. Otherwise, I'm going to real quick show you about the homework that we'll do for Friday. Oh, excellent, Kathy. Way to go. So for Friday, you'll be getting an automated email if you have never joined learn.parallax.com. You'll see an automated email saying that you have an account that's been activated. Then you'll also get an email from Stephanie that has some instructions. And I think this is either way. Basically, let's see. No, this is so basically what I want you to do is log into learn.parallax.com. If you've never done that before, you'll get an email, probably an automated one, saying that you've been added, and then you'll also get an email from Stephanie. Now, for anybody who already has a learn.parallax.com educator account, and these are educator only accounts, you can go to learn.parallax.com, and to log in, just click educators, and then there's a login link right at the top. Right there. And when you log in, it will look like this. And if you happen to have forgotten your password, there's a request new password button. And don't worry too much if you're unable to log in. Like, for example, if you request a new password and your district spam filters it for some reason, do email Stephanie or me, and we'll help you out. Don't worry too much if you can't get this going. It's a goal to have it ready by Friday, but it won't affect your ability to participate in the hands-on part of the workshop. And then the other one is what I'd like you to do is the same thing we just did with the whiskers, which is we built the circuit, and then we tested it. And that way we knew we were ready. And so what you'll end up doing is there'll probably be some circuit mistakes, but here's the build the infrared circuits, and it's going to have you, as we did earlier, it's going to list the parts. You'll have some resistors with color codes, infrared detectors, infrared LEDs, little containers to put the LED in. They're called standoffs and shields, and some jumper wires. And when you're selecting the infrared LED, it's a clear, it's got a little clear plastic thing on top, but there are two different shapes of clear plastic things in your kit. You'll want the taller, more dome-shaped one. Those are infrared LEDs. The shorter, more snub-nosed one is a photo transistor, and I'll tell you about those a little bit on Friday. And it'll show how to put the infrared LED together, and you'll want to make a note of which is the longer and which is the shorter pin. And then it'll show you the circuit both in schematic form and in wiring diagram form. And you'll want to go really carefully with the wiring diagram. And where it says here anode lead, that is the longer lead. So you'll have the longer lead going to the anode lead. And when I send the email out, I'll add a reminder about that the anode lead is the longer of the two leads of that infrared light emitting diode. So this is the circuit you'll build, and then we'll have you go to the next page with it, which is testing. And it's the same thing we did where it has a script, and it's first going to have you test one of the pairs, and then you'll go ahead and update it. Oh, this is both of it. So we'll have you just run the script at the very bottom of the page. So I'll add a note about that in my email that basically this will test both infrared detectors, and it'll tell you whether they both work. And you'll be looking at the little lights. We've already done the P20 light. That's an amber light at the bottom of the breadboard, and there's also a P21 light that's a second amber light, and we'll use those to tell whether an object has been detected or not. And I don't remember off the top of my head whether the light turns off when you detect infrared or whether it turns on. I want to say that it turns off, that it's active low. So if you put your hand in front of the, if you put your hand in front of this infrared circuit right here, like if you put it 2 or 3 inches away so that this little infrared flashlight is shining at it, the corresponding light will turn off. That'll be P21 for the right and P20 for the left. I might have that backwards, but basically you want one state when you have your hand in front of it and the other state when you take your hand away. And so go ahead and test it and email me if you, and generally, if it doesn't pass the test and there are checklist instructions, you'll want to just go through and very carefully recheck all the different connections that you've made and made sure they match the wiring diagram. And so back to here. Yeah, so essentially the light will be on when you have not detected something, and it'll turn off when you have detected something. So again, running this script. No, that's the wrong script. I apologize. It's down at the bottom. Build the IR circuits. Here it is. Test the IR object detectors. And so, so again, you'll run this script and the amber lights should both be on when nothing is detected. So like if you pointed at the ceiling, and then when you put your hand in front of one of them, its corresponding light should turn off. And so that is your homework. And I've got that also in slide form if you want to use the slide. I don't know which one is going to give you a better view, zooming in on the web page or looking at the slide, but they're both available to you. And then a final reminder for today is that when you are done, unplug that power plug so that your robot doesn't drain power overnight. And so thanks for coming, everyone. Go ahead and stay with us if you want to talk about any particular education topics or get some tech support after this session. This, though, concludes the recorded portion of the workshop.